about how to express displacement over the length as displacement u1 and shape function 1 plus displacement u2 times shape function 2. Okay? So from this expression, we already know what we're going to solve. Okay? What is common and not changing is a shape function. What is changing is the normal displacement. Normal displacement is the norm. Okay? So in that way, we don't worry about this interpolation anymore. Okay? So if you go back, you can do this by solving the boundary condition. Okay? But this is telling you the same thing. In this case, this is a linear function expressed as a0 plus a1x. Okay? This linear function must fulfill the boundary. What is the boundary? When x equal to 0, the displacement is equal to u1. Then x equal to L, the displacement is equal to u2. So then I can do the solution for a0, a1. Okay? This is almost like telling you or presuming you haven't learned any secondary school geometry. Okay? But what we did, if you learn about the line equations, this is simply the re-expressions. Okay? I would prefer you to treat it as a re-expression. I don't bother much about. Okay? But the important thing here, why people have to use this step to get the shape functions, because there is a certain assumption that this whole method developed is trying to fulfill the boundary. So finite element method is to solve the boundary value problem. What's boundary value problem? The boundary value problem is if the boundary is given or fixed, you should be able to do interpolations quite good to fulfill the boundary. Okay? So anything that fulfills the boundary is one of the possible solutions. They could possibly deviate it from the real, but it's not bad as an interpolation. So that's why, so in the textbook, usually they don't use your linear interpolation straight away from the line. They will start from a linear function, application of the boundary. Substitution of the boundary is using displacement we want to do. Okay? So how do you treat the problem just now? Okay, if I having the idea of dividing the rod into 3 segments. Okay? Okay? If this is the U1 and this is the U5. Okay, they are basically doing this division. Okay, you might know that you can possibly take the interpolations. Okay? But in reality, in the presence of loading, your answer to deviated. This is also a possible answer. This is another possible answer. Okay? So what finite element do is they will take you the small element. Your element length must be as small as possible or mesh to be as small as possible, so that this error is minimal. Okay? So here the whole idea of boundary value is it depends on the two elements, on the end of the two nodes. Then you try to find the unknown. Okay? And then next, what do we go next? Okay. If you can express the displacement as a linear function, then we can come back. Okay. Displacement is shape function times u1, shape function n2 times u2. So this is the shape function is the range of your inference. And some more, they have the so-called linear interpolations. At the point where you set it is 1, at the next neighboring point is 0. Okay, so this is your n1. The n2 is the other way around. So now, I'm going to re-express my shape functions into matrix form. Okay, and I'm going to define the strain is the B matrix times U. Okay, so this is the complication, but then we try to do it. Okay, we have derived this. So let's do the re-expression again.同学看到没有？你刚才写的这个叫做这个位移场 ，This is your what you call your displacement field. It is changing along the length, and you also, if you plot this U versus position, okay, then immediately you know what is your strain. Your strain is du dx. Strain is the space gradient of displacement. Okay, space is your location or your position. What is the displacement? Displacement is your movement. Okay. So in this case, since we know U1, U can be expressed as U1 N1 plus U2 N2. So if you are doing the space gradient, the only thing that changes with the space is the shape function. In the case of boundary value problems, U1 U2 is fixed. 所以你可以想象，你人在一个人群里，你触手可及的，你的影响力就是你的邻居。你可以推你邻居一把，他再推人家一把。OK， 所以你的位移跟你邻居的位移，就定义你大概的位置。OK， in the case that when you try to find out the relative displacement. So the strain, you got to differentiate the shape function. But not the displacement. Okay? So this reduces your problem to be boundary value. Okay? The only thing changed is N1. N1 is this rule curve. This is the rule curve. What's the gradient? If you do differentiation of the N1 dx, then you have U1 times minus 1 over L. And then next, what about the gradient of N2? The gradient of N2 is 1 over L. So in this way, then you already can finish the expression. But now, for the purpose of doing matrix analysis, we're going to rewrite them in the matrix form. So you can write this as your strength is du dx. Can now be expressed as dn1 dx, and then what's that? And then dn2 dx. And then you do the sum. So this is your so-called your E matrix. It displays gradient of your shape function times your displacement vector. Yeah. After having this step, we can bring these to your total potential energy expressions. Remember, our total potential energy is the strain energy minus the positive work done. And then in the strain energy expressions, you have the stress times strain, and then integration of the space minus the positive work done. In this case, because we can derive the strain is the sum of gradient of shape function times displacement. Okay, then the stress is just a Young modulus times the strain. Okay, so if you go step by step, stress times strain can be expressed as Young modulus times strain squared, and then the strain square is what? The strain square is space function gradient times displacement sum squared. And if you do the expansion, the first shape function gradient times displacement 1 squared, and then next plus shape function 2 times displacement squared. And then they have their cross multiplications, which is 2 times the gradient of first shape function times gradient of second shape function times first displacement and second displacement. So that's not all, because next what we're going to do is, this is just the strain energy expressions. What you're going to do next is, you're going to do the gradient. Okay? In the case of the gradient, you are going to have the force balance. And if you do it twice, you are able to find two equations. And that two equations will lead you to the, what you call the stiffness matrix. Okay, let's try to do it by hand, so that you have a better idea. So we have this expression already. So let's find the strain expression is Young modulus the strain squared. So if you now do multiplication, so this is going to be dn1 dx u1 plus dn2 dx u2, and then you square it. Okay. Then you have e, and then the square of this expression. in this case, if you're going to write the equations for the spring, you can write this as strength energy minus F1 U1 plus F2 U2. And this strength energy can be expressed as sigma epsilon A dx. Okay. If you take this example to find displacement force 1, then what you have to do is you have to do the differentiations of this whole expression with respect to U1 and then minus F. And the second equation will be the differentiation of the stress energy density and then minus F. Okay? So here you know what's the operation because the left hand side is 0, you will move your force to the other side. Then you already can write the equation. This is your F1, F2, that's your force vector. And then what is your right hand side? Take this example. If I just forget about the matrix expression, I just do the differentiation. First, rho is to do the partial differentiation with respect to U1. So I'm going to have 2 dn dx, dn1 dx squared, and U1. And then next, okay, I have my 2 dn1 dx times dn2 dx times U2. The last term is 0 because for partial differentiation of U2 squared with respect to U1 is 0. And then next, we write the same expressions, but partial differentiation with respect to the U2. This is something 0 because partial differentiation of U1 squared with respect to U2 is 0. 所以你拿 U1 对 U2 做偏离分，那是0。Okay. 然后 U2 对 U2 没有任何意义。So in this case, so you have the second rule being these expressions. And then the last one is going to be 2, and then what do you have? Your dn2 dx squared u2. But this whole expression, not to forget, you are doing the integrations with respect to the space. Okay, this whole thing will be integrated with respect to the length. Okay, in this way, you manage to get what? You manage to get a stiffness matrix. So how this stiffness matrix is to be expressed? If I do a rearrangement, take everything here. This can be re-expressed as a stiffness matrix times unknown displacement U1, U2. So in this case, you might think this is something complex. But remember what is your gradient? If this shape function 1 is minus 1 over m. And what is the shape function 2? 1 over m. And then here, energy form divided by factor 2. So in this way, you'll be able to find after the operations, you have your, and somehow you have the integration with length change from 0 to L. Then you eventually is going to give, you're going to obtain 1 minus 1 minus 1 1 times EA over L times displacement U1 U2 is giving you force 1 force 2. Okay. So what this tells you, finite element is an exercise for mathematicians. Structural analysis has been there. People have known about energy method. People have known about total potential energy method. But you're going to re-express all this into the matrix multiplication with the displacement vector. So this is going to be the, in the end, lead you to the same expressions. Okay? Not a surprise, but the method can be generalized. 所以你有5个定律，你有能量法，那你还做这些做什么 ？Okay? One of the important things why you need the energy method more than Hooke's law is in this operation, what was introduced to you? In this operation, what was introduced to you is the energy method, okay? And the strength energy, okay? And then the next thing introduced to you is the displacement is a linear function or the space function, okay? So this laid the foundation of extrapolation to other fields. Because in the multiple physics field, you have energy coming from in the form of heat. Okay, that is due to temperature gradient. You have energy due to the electrostatic field. That is due to the potential field. So long as you can express the thing in the energy form, and your variable, either temperature or potential, can all be interpolated. This method will work equally well to electrostatic field analysis or temperature field analysis. Not just this, even the flow field and pressure field, if you want to do the calculation for the flow analysis. Okay? So that's the beauty of the energy method. It works across the field. Okay? We are not doing something redundant, we are just generalizing. Okay? But these generalizations must be reduced to your Castigliano theorem or even Hooke's law. So, in 能量法的目的是，你可以在不同的场，实力场、静电场、热场、压力场都能运用。只要你假设这个场是连续的，然后你带入能量法，它就有办法帮你找到力。Okay, so that's the whole idea. By using the displacement field and energy method, you'll be able to find out the force. The force can be piezo force, magnetic force, any force. Okay. And then next. So the reason why I have to write it down is just to remind you, you also have to do the same. For this course, don't read equation. Equation got no meaning. You have to practice it by yourself. Okay? 这门课不是用读的，是你直接上哪节题 ，OK？ 然后把一般的方程式写成矩阵的形式 ，OK？ Okay, with this, then we'll be able to write these two equations. Pretty straightforward. Okay? And in summary, we are able to express strain in terms of displacement. We are able to express stress in terms of strain. Multiplication of the two divided by multiplication of stress and strain divided by 2 will give you strain energy per volume. You can do the integration to find out the total strain energy. We now do the partial differentiations. You will be able to find out the force. Okay? And then next, we calculate to the something equation. How do we find out the distributed force? Okay, in this case, the stress energy part don't change, but it is the work done by external force. There are two types of external force. There could be a normal force, then you simply a normal force and the displacement to do the positive work. But for the uniform, or so-called the distributed surface force, you have to multiply it with the local displacement. Okay? So this local displacement, now you have to do the interpolation. Okay? Okay, here. Now let's consider the linear interpolation we did before. 所以你这个位移场也是用线性内差去跟它做一个预测。So in this case, how do you calculate the work done by distributed force? Okay, distributed force in this case, because you are doing the linear interpolation in our toolbox. Okay. So now let's draw the note. Okay. In the case of a 2D element, you possibly have the displacement U1, U2. So in the plot, you can plot x versus displacement. This is the U1, U2, starting from x equal to 0 and ending at x equal to m. Likewise, okay, just now we tell you before, if my distributed force is uniform, that's very easy to find out the lump force. 所以这个力怎么算？你说要把它丢到两个这个节点上，你的力基本上是 F1 is equal to QL over 2, F2 is QL over 2. In the case of linear, so-called the uniform force. Okay, however, if the force is not uniform, then you have to do something. Okay, so when you get this force on the right hand side, remember this? We got this force on the right hand side by writing the derivative of the positive work done. You are remember this? In this equation, right hand side is the force vector, left hand side is the stiffness matrix, and displacement vector. So what you write on the right hand side, the displacement, the force vector are straightforward, F1 and F2, that's it. But what happens if now if you have the distributed form? If you now have distributed force, the force done, the work done by the distributed force can now be written as Q U dx. Okay? As we tell you, U can be written as, it is a space function, it is U1 N1 plus U2 N2. Both N1 and N2 are the shape function. Okay? So what you can handle for the force, just now I tell you is a constant. But indeed, it can be also expressed as a linear function. Okay? So if that's the case, what is the work done? Okay? Your work done can now be expressed as, if you do multiplication of these two, okay, what do you have? You're going to have U1 Q1 N1 squared plus U1 Q2 N1 N2 plus, what do you have? You have your U2 Q1 N1 N2 plus U2 Q2 N2 squared. Okay? So remember, this got to be integrated with the length. Okay, but remember also this. What you have to find out the force here. The force, the equivalent force on the right hand side is the partial differentiation. If you now want to use it to find out your F equivalent 1, okay, then you are going to do the differentiation. Okay. Okay. So with this, if I'm going to do the partial differentiation with respect to U1, the first term is going to Q1 N1 squared. Second term is, what you have is your Q2 N1 N2. Does it have to do with the second term? No. How about the equivalent? But remember to do your integration. How about your equivalent force at the node 2? It is your Q1 N1 N2 plus Q2 N2 squared dx. Okay? So this is how you obtain the distributed force. Okay? So your force now can be added to this side. Okay? Without changing your stiffness matrix. So for your ease of understanding, please understood the operation with scalar. Okay, matrix is just a real expression. If a scalar word, then you are there. Okay? So this is how we did with the calculations. Okay, we did it already. Okay, how about the distributed force calculation? You have your U being interpolated, Q, the distributed force being interpolated. Please do the multiplication to find the work done by distributed force. And then now your F1 can be obtained by this partial derivative. Okay, then you find out how it's related to your function. Okay. with this, now you can see the two examples. So your F1, F2. Okay, in this case, this is a constant Q naught. That's easy. So this is just divided by half. Yeah, Q naught over half. Okay. I think, yep, with this then we know some basic. Okay. Yeah, so far so good. Okay. Yeah, no questions. Then I'll just kind of like give you some. We cover one more. Yeah, just give you a preview. We're not going to finish all this. Okay, next week we're going to cover this part, but today I'll give you a preview. So what we learned today is energy method. One thing we do there is we know that the displacement is continuous. And then the displacement got to fulfill the boundary condition. What can be interpolated? Okay, yeah, you can use any function you have. Okay, so far we are using linear function. But in later, in the case of gate bending, you are using some bilinear, you are using quadratic interpolations. So let's further generalize what we learn. If you are in a club, okay, either you can work with 2 persons or 3 persons. If you are working with 2 persons alone, okay, if you are a single person, your reach is only one-sided. Okay, if you try to push. But if you work 2 persons in a group, okay, then it is possible to have some choreography. You can have different pattern of motion. Likewise, if the case of the field is more complex, you can have parabolic function to fit. So here, this is our generalization. The displacement field is going to be continuous between 2 bounds. And then, in the case of your boundary, okay, we try to reinforce it to be 0 if it's homogeneous boundary. And then in that case, your any function that's in the red can be interpolated by any function that fulfills the boundary. Okay, so that's the whole idea about weighted residue. So this interpolation, is it real? Is it accurate? Okay. Previously we learned about Newton's law. We know force summations at each node. Force is 0. But in the case of numerical calculations, I can't make sure force is balanced. So what I can do best is I can do the minimization. Okay? So how do I minimize? There could be error using function 1. There could be error using function 2. How could I do the minimization of the error? So what I can do is I can do this minimization by a weightage. And what's the weightage I'm using? Okay, I can say half, that's fine. Okay, but people come up another weightage. That weightage is using the same shape function you use as weightage for error minimization. So this is going to be the residue method that we're going to cover. Okay? So for here, so we can use any partial differential equations or any differential equations. This is the differential equation that has an answer. Okay, I can show you the analytical solution. What's the answer of this second order differential equation? To find out the answer, you just do the integration once, then you have a gradient, and if you do the integration twice, then you have the exact value. So this integration will give you y is equal to a cubic function plus a square function minus a linear function. Okay, that's the exact answer. How to obtain this? You have to sub in the boundary conditions. The boundary on the left hand, the boundary on the right hand, what are the values? And in the end you find out the coefficients C and D. So this is the way of calculations. Okay? But in the case of my weighted residue method, okay, I don't do that. Okay, what the shape function I do? The shape function I do is, if I know the boundary, okay, if I want to fit the boundary, okay, if this is coordinate x equal to 0, and this coordinate x equal to L, how do I make sure the function is fulfilling the boundary of 0? Okay, there are many possibilities. Okay, but one of the clear possibilities is I can define the function as what? I can define the function as x equal to 0 and x minus L. These are the two interpolations I could have. So what's my guess solution? My guess solution will be the constant times x minus 0 and x minus L. Okay? If I take these and then I do the second order differentiations, first order differentiations give me 2c. Okay, this is going to be x squared minus Lx. This is 2c, 2x minus L of c. If I do second order derivative, I got 2c. Okay. If I now do the substitution of that so-called the gradient into my equation of motions, and now I pre-multiply it with my weightage. This weightage is my shape function. Okay? Then I can minimize it. How do I minimize it? I minimize it by the, just after integration, then I set it to 0. Because currently I have only one unknown coefficient C. So I can change my C to fit the value to force the residue to 0. So in that way, then it is possible to find out an alternative solution. These alternative solutions, okay, is what we call Gaussian method. Okay, it fits quite well to the exact solution. Okay, but there is some condition. This condition is what they call, it must be a boundary value problem, which is set. Okay.